So welcome to lesson 7, applications of exponential functions. There are really 3 types: half-life, exponential decay, doubling period, exponential growth, as well as generalized growth and decay. We're really only going to focus on the first 2, so half-life as well as doubling period. You should be able to kind of picture exponential growth and decay using the graphs we looked at last time. So here, when the b value is a whole number, we see that the function is always increasing. This represents exponential growth. So if I look at every y value, so as the x value increases by 1, so here when you go from 0 to 1, the y value doubles. When you go from 1 to 2, the y value doubles again. 2 to 3, the y value doubles again. And so that's why we're going to see an exponential growth, because each time we increase the x value, the y value doubles from its previous value, which means it can grow very rapidly. Similarly, this would represent exponential decay because, again, the b value is a fraction, which means it's always decreasing. And so we see kind of a similar pattern, but the opposite. So each time I increase the x value by 1, so when I go from here, where x is -3, versus here when x is -2, we see that the y value drops by half. Then from -2 to -1, the y value drops by half again. From -1 to 0, the y value drops by half again. So this represents exponential decay because it's decaying at a very fast rate. The y values are dropping by half each time. So again, this represents exponential growth, where it's going to grow rapidly. Here is exponential decay, where it's going to decay rapidly. So we're going to look at 2 specific examples: half-life, which is exponential decay, as well as doubling period, which is exponential growth. So what is half-life? If you took chemistry, this should be a review. If you haven't, let's learn it for the first time. Radioactive atoms have unstable nuclei. So remember the nucleus. Every atom has a nucleus. That's where the mass of the atom is. It houses the neutrons as well as the protons. Radioactive atoms have unstable nuclei. So radioactive atoms are the things that when we hear of radioactivity, the atoms that essentially release this radioactivity are called radioactive atoms. And they have unstable nuclei. The nuclei are not stable. They want to constantly break down. So in an attempt to become more stable, these radioisotopes decay by emitting radioactive particles. So in other words, the nucleus is unstable. It's going to constantly decay or break down in an attempt to become more stable. And as it decays or breaks down, it's going to release radioactive particles in the process. As they do this, the mass of the radioactive atoms decreases. So the mass decreases. So as you can imagine, we have an unstable nucleus. It needs to break down to become more stable. As it breaks down, the mass of the radioactive atoms decreases. Radioactive atoms decay at a predictable rate. So they don't just randomly decrease or a random amount decreases. Rather, we have something called the half-life. The half-life of a radioactive atom is the amount of time that is required for a radioactive sample to decay to half its mass. So what does that mean? So let's say we have a radioactive element and it starts off at 10 grams and decays to 5 grams. So we call that it's decayed to half its amount. And the amount of time that it's required to decay to half its amount is called half-life. So if it takes 2 minutes to go from 10 grams to 5 grams, that is its half-life. Within 2 minutes, a mass of that radioactive element will decay to half its mass. So again, the half-life of a radioactive atom is the amount of time that it's required for the radioactive sample to decay to half its mass. So here is a typical question that you'll see with half-life. We're going to try to imagine this question. We're going to try to solve it using logic first, and then we'll look at the equation and see how it fits in. So it says radium-221. I'm going to always list an element as well as its mass. All you need to know is that's the radioactive element. You don't need to know any like chemistry knowledge to solve these problems. So radium-221 has a half-life of 30 seconds. Because it has a half-life, again, you can deduce that this is a radioactive element. So it's radioactive, it has that unstable nucleus. That nucleus is constantly breaking down to become more stable, and its half-life is 30 seconds, which means it takes 30 seconds for a mass of radium-221 to be decreased to half its mass. How much radium-221 would be left over after 90 seconds if the initial sample had 50 grams of radium-221? So let's try to solve this logically. So it says the initial sample had 50 grams, so I'm just going to draw a picture to represent this. The mass here is 50 grams. We know, based on the half-life, that every 30 seconds, the mass will decrease to half its mass. So what does that mean? Let's take a look at the first half-life. So here, let's call this t is equal to 0, because that's what we have at time is equal to 0. At time is equal to 0, or at the beginning, our sample had 50 grams. 30 seconds later, so let's represent that. 30 seconds later, so I'm going to call this 0 seconds actually. So 30 seconds later, we know that's the half-life. So this mass should be cut in half. So instead of having 50 grams, we now have 25 grams. So that's what half-life represents. Every half-life, every 30 seconds, the mass of the sample will become half. So the question here was how much radium would be left after 90 seconds? Well, after 30 seconds, it reduced from 50 to half its mass, which is 25. What happens 30 seconds later? So 30 seconds later, the time would be 60 seconds. And because another 30 seconds, or because another half-life has passed, the mass of this will reduce by half again. And you'll notice that I'm actively trying to reduce the picture by half as much as I can in order to visually show this. So half of 25 grams is 12.5 grams. So again, what has happened? At 0 seconds at the beginning, we had 50 grams of radium-221. 30 seconds later, a half-life later, its mass halved. Then 30 seconds later, its mass halved again. But we want to see how much would be left after 90 seconds. So we have another half-life to get through. So another half-life later will be at 90 seconds. And again, the mass will be cut in half. And half of 12.5 is 6.25 grams. So what have we seen? We started at 50 grams. A half-life later, it became half, 25 grams. Another half-life later, it became half of this, 12.5 grams. And another half-life later, 12.5 divided by 2, 6.25 grams. That's how half-life works. So whatever mass you're at, every half-life, the mass will decrease by half. So this is what we have. This is an easy way to solve the problem. We saw the logic behind it, but what's annoying is I have to draw these pictures and calculate the mass at each time. So what someone has done is they've summarized all this information into a formula. So the formula is A is equal to I half to the power of T over H. So this entire thing is the exponent for the half, and this is why it's an exponential decay. Remember, when you have a fraction as your b value, you're always decreasing or decaying. And because it's an exponential function, it's an exponential decay. So with this formula comes 4 different variables that you need to know. I is the initial mass. So this is the initial mass. What is the mass of the radioactive atoms that you started off with? The A here is the mass of the radioactive atoms left after time t. So in this particular scenario, I would have been 50 grams because that's how much we started off with, and A, amount left after a certain amount of time. So after 90 seconds, the A would be 6.25 grams. After 60 seconds, the amount left would be 12.5 grams, and so on and so forth. So the I represents how much you started off with. That's always going to be the same. The A represents how much is left over after a certain amount of time. So if we were looking at 30 seconds, the amount of the 50 grams that was left over was 25 grams. After 90 seconds, the amount of the 50 grams that was left over was 6.25 grams. The units of A and I must be the same. In this case, we were measuring the masses in grams, so we kept it grams. If we were measuring in milligrams, we'd keep it milligrams, so on and so forth, as long as these units are the same. Next, we have T and H. The H here represents the half-life of the radioactive atoms. So in this case, the half-life was 30 seconds. And T represents the amount of time that actually passes by. So here, T would be 30 seconds. 30 seconds passed by. Here, T would be 60 seconds. 60 seconds passed by, and so on and so forth. Again, just like how the units of A and I must be the same, the units of T and H must also be the same. So these two should have the same units, and these two should have the same units for this to work. So what I want to do is I want to use this equation to represent these different scenarios, just to see how this equation works. So let me just take out a color. So let's start with this. The amount that I expect to get is the initial amount, which is 50 grams, times half to the power of T. T here is 0 seconds, divided by the half-life, which we saw was 30 seconds. So both of these were measured in seconds, so that's fine. And the amount here is, the initial amount is grams, so the final amount will be grams as well. So that just gives me 50 half to the power of 0, because 0 divided by 30 is 0. Half to the power of 0 is 1, so 50 times 1 is 50 grams. So what does this tell me? I started off with 50 grams, the T was 0, 0 seconds later, so right now, I still have 50 grams. Let's take a look here. So again, I start with A for amount. The initial is still 50. I started with 50 in all of these. The initial stays the same. I do half, then T divided by H. The time that has passed is 30 seconds, and the half-life was also 30. So now I have 50 half, 30 divided by 30 is just 1. So 50 times half, which is 25 grams. So again, it gets me the same answer that it was able to depict with this image. Here we have 30 divided by 30, which is 1. What this 1 represents is how many decay periods has passed, or how many half-lives have passed. So here the half-life was 30 seconds. We've passed only 30 seconds, so we've passed 1 decay period. Let's try it with this. So we have amount is equal to, again, the initial always stays the same. That's how much I had at T is equal to 0 seconds. I do half to the power of, now 60 seconds has passed, so T is 60, divided by my half-life, which is 30. So that's 50. Half to the power of 60 divided by 30 is 2. Again, what that 2 represents is 2 decay periods. So if you started at 0 seconds and went to 60 seconds, you passed 2 30 seconds, or 2 half-lives, or 2 decay periods took place. If I was to simplify this, this would be 50. Half to the power of 2 is just a quarter, which gives me 12.5 grams. And let's do it with this last one. A is equal to 50. Half, the T here is 90, divided by H, which is 30. So I have 50, half to the power of 3, which is 50. Half to the power of 3 is 1/8, and that gives me 6.25 grams. Again, the 3 represents 3 decay periods, because each decay period is 30 seconds, and we've passed 90 seconds. So we can see that the formula works well. I can use this formula to determine exactly how much of the radioactive element I have at any given time. So that's what we're going to do with these examples. So example 1, an example of strontium SR90 has a half-life of 25 years. What does that mean? That means it takes 25 years for a certain mass of strontium-90 to be reduced or decayed to half its mass. Find the mass of strontium-90 remaining from a sample of 80 grams after 125 years. So you see that in our formula, we have 4 variables, which means we will be given information for 3 of them. We need to find the last one. So let's read carefully. It says an isotope of strontium, SR90, has a half-life of 25 years. We know H represents our half-life, so let's write that in. H is 25 years. I want you to write in the units as well, because remember, these 2 units have to be the same, and these 2 units have to be the same, or we need to convert them before we use them. So we've taken care of this number. Find the mass of strontium-90 remaining from a sample of 80 milligrams after 125 years. So the half-life is 25 years. We know the time that's passed is 125 years. And we're trying to figure out what is the mass after 125 years. In other words, we're trying to figure out the amount, but we know the initial amount was 80 milligrams. So we had 80 milligrams of strontium-90, and we want to know what the mass would be after 125 years. So we have the initial mass, we want to find the mass of radioactive atoms left after time t, which is 125 years. So let's write the general formula. A is equal to I half to the power of t over h. We can fill in our numbers. Again, before you do anything with the numbers, make sure that the units are correct. These 2 units are the same, that's fine. This unit is in milligrams, which means your final answer A should also be in milligrams. So once you have this, plug in the right numbers. So we're trying to find A, so I'm going to leave that as A. I is 80. I'm going to copy the half, and then T over H is just 125 over 25. Okay? So now that I have this, I'm going to simplify it. When you simplify it, always simplify the exponent first. So I have 80, half, 125 divided by 25 is 5. Then A is equal to 80. 1/2 to the power of 5, again, you should be comfortable with this, is 1 over 32. 2 to the power of 5, you should know that that's 32 by now. And then we just have to simplify. So here we have a multiplication of fractions. So I'm just going to copy this down before we simplify. So 80 is the same thing as 80 over 1. And we're just going to simplify, because with multiplying fractions, we can simplify this way, as well as diagonally. This cannot simplify. This cannot simplify. I could divide both of these by, I could do 2, but I can also do 4. I could do 8. And I can also do, I'm thinking 16, yeah. So if I divide 32 by 16, that's 2. And 80 by 16, that's 5. Let me just make sure. 0, 3, 80. Okay? So now what I have is amount is equal to 5 times 1, which is 5, divided by 1 times 2, 2. So amount is equal to 2.5. Again, make sure the units stay the same. It's milligrams. Because this is a word problem, remember you do need to write a sentence. So 2.5 milligrams of strontium-90 would remain after 125 years. Okay, let's try the next question. Radium-221 has a half-life of 30 seconds. So we've seen radium-221 already. So it's a half-life of 30 seconds. At the end of 180 seconds, there were 2 grams of radium-221. How much radium-221 was there initially? So the question follows the same format. We're going to be given 3 of the 4 variables. We're just going to solve for the other one. So let's read the question again and fill in the information we know. Radium-221 has a half-life of 30 seconds. So H is 30 seconds. We know that. At the end of 180 seconds, so this is my time, the time that's passed, 180 seconds, there was 2 grams of radium-221. Okay, so at the end of 180 seconds, there was 2 grams of radium-221. How much radium was there initially? So we don't know the initial amount. So I is the question mark in this case. And the A, the amount that was left over after 180 seconds, was 2 grams. So we're going to write the general formula once again. Again, look for the units. T and H have the same units, that's fine. Here, amount is grams, so we know that the initial amount will also be measured in grams. So let's plug in the numbers we have. So here we have an amount, which is 2 is equal to, I don't know what my I is, half. T over H is 180 over 30. Again, simplify by simplifying the exponent first. So 2 is equal to I. Half 180 over 30 is 6. 2 is equal to I. Again, 2 to the power of 6 is something you should know off the top of your head now. So 1 over 64. And let's simplify this. So on the side here, the right side, I'm just multiplying fractions. So I times 1 is I over 64 equals 2. And I want to isolate for I, so I'm going to multiply both sides by 64. These cancel out, and what I'm left with is I is equal to 128. Okay, so I is equal to 128. Again, we need to measure in grams because the amount was measured in grams. So I is equal to 128 grams. Don't forget to write a sentence at the end. There was initially 128 grams of radium 221. Okay, so we'll do one more example, and that's half-life. So give me 2 seconds as I switch to the next sheet. Okay, so the last example here, Neptunium-240 has a half-life of 1 hour. Find the mass of Neptunium-240 remaining after 5 hours if the initial sample had 128 grams of Neptunium-240. So let's fill in the information that we have first. So Neptunium-240 has a half-life of 1 hour, so I'm going to write that in, 1 hour. Find the mass of Neptunium remaining after 5 hours, so T is 5 hours, the time that has passed, if the initial sample had 128 grams. So they told us the initial, the I is 128, and we want to find the A. Okay, so again, once you have all the variables, the first thing you should do is check to make sure that the units are okay. These two have the same units, that's fine. These two will have the same units, so you know A will be written in grams. So write the formula, A is equal to I half T over H. Now we can fill in the values that we have. We don't have A. The initial amount is 128. Here we have half to the power of T, which is 5 over 1. So that's the same thing as 128. Remember, you always want to simplify the exponent first, half to the power of just 5. We've seen 2 to the power of 5 before, so this is just half 1 over 32, so half to the power of 5, so the denominator is 2 to the power of 5. And if I divide this, 128 over 32, that's just 4 grams. Again, we went with grams because the units had to stay the same. So write a final sentence. The amount of Neptunium-240 left over after 5 hours is 4 grams. Okay, so to practice these half-life questions, you are going to do handout G number 3 to 5. I'm also going to, in another video, show you the second application, which is exponential growth.